Hello, Chem 1 class. This is me going over the study guides for chapter 5. Okay, hopefully I won't make too much of a butt out of myself when I go over this. I'm posting it on YouTube. So, yeah. Alright, so yeah, I guess I'll just go ahead and get down to work. So, let me go ahead and minimize me. Let's see what we got here. Okay, I guess you guys don't really need to see me at all, do you? Uh, Okay, so let's get this show on the road. All right. So number one, an endothermic reaction causes the surroundings. Of course, it's not going to warm up because that's what an exothermic reaction does. Become acidic? No. Condense? No. Decrease in temperature? Yes. Okay, that's what the endothermic reaction does. It's going to cause the surroundings to decrease in temperature, and E says release carbon dioxide. We know that's not the case, right? Uh, Number two, an exothermic reaction causes the surroundings to warm up. Of course, yeah, that's what the answer is going to be, warm up. So the answer to number two is, of course, A. Of course, you could see that from the answer key at the bottom of the study guide. Number three says copper metal has a specific heat of 0.385 joules per gram per degree Celsius. Calculate the amount of heat required to raise the temperature of 22.8 grams of copper from 20 degrees Celsius to 875 degrees Celsius. Okay, I'm going to go ahead and snip this, and I'm going to go to my whiteboard. Let me see. I'm sure you guys can tell that I don't have Windows 11 because the snipping tool for Windows 11 is different. It's, I guess it's more sophisticated. So let me go to my whiteboard, and I'm going to go ahead and paste that. And let's see, let's go ahead and minimize this. Now, what I didn't do is I didn't include the equations. I guess I should do that. If I remember, I'll go ahead and include the equation. All right. So it says copper has a specific heat of 0.385 joules per gram per degree Celsius. Calculate the amount of heat required to raise the temperature of 22.8 grams of copper from 20 degrees Celsius to 875 degrees Celsius. So we have two equations to work with. I'm going to say that Q is equal to M times C times delta T. Okay? And I'm also going to say that delta T is equal to T final minus T initial. Okay. Now, of course, they tell us what the specific heat is. It's 0.385 joules per gram per degree Celsius. That's C right here. That C is the specific heat, and they want us to calculate the amount of heat required. So that's Q. So we're going to try to find Q. They give us the mass of 22.8 grams. Okay, and they give us the change in temperature. So T final is 875 degrees, and T initial is 20 degrees Celsius. Okay, so it's not that hard for you to figure out that delta T is going to be 875 minus 20 degrees is going to be 855 degrees. Okay, so we already have delta T, so that's what we're going to put right there for delta T. So all I have to do is say Q is equal to my mass, which is 22.8 grams. Okay, times my specific heat, which is 0.385 joules per gram per degree Celsius, times delta T, which is 855 degrees Celsius. Okay, so now what I would like you guys to notice is that I used units, didn't I? The sky didn't fall and the world didn't come to an end. So let's see what units cancel out. Degrees Celsius cancel out. I have degrees Celsius in my delta T term, and I have degrees Celsius in the denominator of my specific heat term. Okay, grams also cancel out. I have grams in my mass term and grams in the denominator of my specific heat term. The only unit I'm left with is joules. So, of course, when I take 22.8 times 0.385 times 855. I end up getting 7.505 times 10 to the 3 joules. Okay, so that's 7,505 joules, or 7.51 kilojoules. Okay, so of course the answer is D, 7.51 kilojoules. Of course, when you convert joules to kilojoules, just divide by 1,000 or move your decimal point to the left. Let's see. That's to the left 3 places. So this would be 7,505 joules. So you move the decimal point to the left 3 places. That would be 7.505. Since it's only good to 3 significant digits, your answer, of course, would be 7.51 kilojoules. All right. So let's go back to, let's take a look at number 4. If 325 grams of water at 4.2 degrees Celsius absorbs 12.28 kilojoules, what is the final temperature of the water? The specific heat of water is 4.184 joules per gram per degree Celsius. Now notice that the specific heat has units of joules per gram per degree Celsius, but they give us the amount of heat absorbed in kilojoules. So you're going to have to change one. You're either going to have to change the kilojoules to joules or the joules to kilojoules. It doesn't really matter which one, but I just decided to change the kilojoules into joules. Okay, so let's go ahead and snip that bad boy. And let's see what we got here. I hope the volume doesn't go out on me. They said the last time I did a recording, the volume went out on me. So let's hope that that's not the case this time around. I'm going to go back to my whiteboard, and I think I'll clear the canvas. And I'm going to paste. Let's see what we have here. For the time being, I guess I'll make that a little smaller. Okay, so again, we have the two equations. We have Q is equal to M times C times delta T. And we also have the fact that delta T is equal to T final minus T initial. Now, since they're asking us to find the final temperature, my first task is going to be to find delta T. So I'm going to use this equation to find delta T. Then I'm going to put delta T in this equation and find T final. Okay, so let's see what we have here. We have to work with. Q is going to be 12,280 joules. Your mass is going to be 325 grams. Specific heat is 4.184 joules per gram per degree Celsius, and of course delta T is what we're trying to find. Okay, so of course what you can do is do your algebraic manipulation before you actually plug numbers in. So I can easily say divide both sides by MC and end up with Q divided by MC is equal to delta T, right? Okay, so that being the case, you'd have 12,280 joules divided by 325 grams. And I'm going to also divide by my specific heat, which is 4.184 joules per gram per degree Celsius. That's going to equal delta T. Since delta T has units, is going to be in degrees Celsius, everything should cancel out except degrees Celsius. And let me go ahead and cancel out some units. Let's see. I have joules in my numerator, and I have joules in the numerator of the denominator, which means they cancel out. I have grams in the denominator and grams in the denominator of my denominator, which pretty much means I have grams in the numerator, so they cancel out. The only thing I'm left with is degrees Celsius in the denominator of my denominator, so that means I have degrees Celsius in my numerator. Okay, which is exactly what I want, since I'm trying to find the change in temperature. So 12,280 divided into 325 equal parts, and I'm going to take that quotient and I'm going to divide that into 4.184 equal parts. And let's see what I come up with. I come up with 9.03. Let's see how this is good to 3 significant digits. Degrees Celsius is equal to delta T. Okay, so now they tell us what the initial temperature was. The initial temperature was 4.2 degrees Celsius. So I'm going to say that 9.03 degrees Celsius, which is equal to delta T, is equal to T final minus 4.2 degrees Celsius. Now, of course, since we're going to end up adding this to both sides, so I'm going to say 9.03 degrees Celsius plus 4.2 degrees Celsius is equal to T sub F. Okay, so of course my answer, since one of these numbers has 2 digits to the right of the decimal point, and the other one has 1 digit, and I'm adding, my answer is only good to, well, 1 digit to the right of the decimal point. So 9.03 plus 4.2 is going to give you, is going to give you 13.23, but we're going to round this to 13.2 degrees Celsius is equal to T final. So let's go ahead and find that. 13.2 corresponds to D, doesn't it? Okay, so the answer to number 4 is D. Right, moving right along. Number 5, a piece of copper with a mass of 218 grams has a heat capacity. Not specific heat capacity, it has a heat capacity of 83.9 joules per degree Celsius. So now when you talk about heat capacity, you're talking about the entire object. When you're talking about specific heat, you're talking about a unit, usually grams of that object, 1 gram of that object. So the heat capacity of 218 grams of copper is 83.9 joules per degree Celsius. Now we want to find the specific heat. Now all you have to do is think about the units, and you'll know how to do this problem. Heat capacity has units of joules per degree Celsius. Specific heat capacity has units of joules per gram per degree Celsius. So I know what you're probably saying to yourself, it can't be that simple. All I have to do is take 83.9 joules per degree Celsius and divide it into 218 grams. Yeah, because you're going to end up with units of joules per gram per degree Celsius, right? So 83.9 divided into 218 is going to give you 0.385 joules per gram per degree Celsius. Okay, and that would correspond to A. It's that simple, guys. It is that simple. Okay, now number 6. Which of these processes is endothermic? Now, first I would like you to think of something that's exothermic. Okay, think of gasoline burning. We know that that's exothermic. All right, how do we know? Because you get hot. If I burn some gasoline around you, you're part of the surroundings and you're going to get hot. You're going to get warm. So that means the surroundings warm up if I burn something. So if you look at A, I'm burning hydrogen. Okay, that's this combustion reaction. I'm burning hydrogen with O2 and I'm getting water. Okay, it's probably the simplest combustion reaction there is because you just have hydrogen. You don't have any carbon around. So I know that that's exothermic. And likewise, C, I know that that's exothermic too because I'm burning wood alcohol, methanol. Okay, methanol is wood alcohol. So I'm burning that, and of course, we expect that to be exothermic. But so we're going to look at B and D. Now, one of these is going to be endothermic. Now, when you look at, remember what I told you guys about latent heat and sensible heat? Okay, sensible heat makes sense. You heat something up and the temperature rises. Latent heat is the heat associated with phase changes. So if I have water at 100 degrees Celsius, liquid water at 100 degrees Celsius, and I want to turn into water vapor at 100 degrees Celsius, I have to put heat into it to bring about that phase change. Okay, to go from liquid to gas. I have to put heat into it. Just since I have to put heat into it to get the phase change, it would be considered endothermic. Now going back the other way, if I have water vapor and it condenses into liquid water, it has to lose energy. It has to lose thermal energy to the surroundings, right? So if I have a gas and I'm condensing it, that would be inherently exothermic, that phase change. So B, I have a gas going to a liquid. We know that, because I just talked about that, we know that that, of course, is going to be exothermic, but D, you have a solid. So water, ice. Ice is converting to liquid water, and of course, in order to do that, it has to absorb energy from the surroundings. So that would be endothermic. So the answer to 6 is D. Okay, so now we get into, let's see, number 7, to which of these reactions occurring at 25 degrees does the symbol enthalpy of formation of sulfuric acid, liquid sulfuric acid, refer? Now, remember, anytime you're talking about the enthalpy of formation, you're talking about forming 1 mole of that thing. 1, so I have to have that thing, and I have to have a 1, the stoichiometric coefficient. So I have to have 1 mole of that thing on the product side. The stoichiometric coefficient has to be 1. It doesn't matter. Even if I have to have fractions on the other side, on the reactant side, it has to be 1. And you're forming it from its elements in their most stable state. Okay, so the most stable state of hydrogen, because we have hydrogen, sulfur, and oxygen. Most stable state of hydrogen would be H2 gas. Most stable state of oxygen would be O2 gas. The most stable state of sulfur would be the solid. Okay, so let's see which one of those corresponds to that. The answer would be E, right? Okay, I have H2 plus sulfur plus O2. And the H2 and the O2 are gases, and the sulfur is, of course, a solid. And I'm making 1 mole of that. Okay, so the answer is E. So just remember that. Remember that. Okay, now let's see if we can do 8. Ethanol undergoes combustion in oxygen to produce carbon dioxide gas and liquid water. The standard heat of combustion of ethanol is negative 1,366.8. So they're telling us the enthalpy change for this reaction. But remember, we're doing the direct method. Okay. Now they give us the enthalpy of formation of carbon dioxide. Okay. They give us the enthalpy is negative 393.5 kilojoules per mole. Enthalpy of formation of water, liquid water, is negative 285.8 kilojoules per mole. And they don't give it for O2, but since O2 is an element in its most stable state, we know the enthalpy of formation is going to be 0. And they want us to find the enthalpy of formation for ethanol. So that should be simple enough. We did several problems like this in class, so I don't think this should be too much of a stretch for you guys. Okay, so here's how we're going to do this. Of course, this is the direct method. So, all right. So this is just like Hess's law, but it's a shorthand version of it. Instead of the products, well, we're going to keep them the way they are. The reactants, of course, we have to flip those around. And in each case, you have to multiply it by the stoichiometric coefficient associated with the reaction. Okay, so I know water, there's a 6 right there, so I'm going to say 6 times a negative 285.8. You can leave the units out. It's understood that it's going to be in kilojoules per mole. And then carbon dioxide is 4 times a negative 393.5 minus, even though oxygen is 0, I'm going to go ahead and include it, 6 times 0 plus 2 times x, which is what we're trying to find, is equal to a negative 1,366.8. Now, most of the time, you're going to be asked to find the enthalpy change for the reaction. This problem, they gave you the enthalpy change for the reaction, and they asked you to find the enthalpy of formation of one of the reactants, okay, which is not that big of a deal. All right, so just be mindful of that, and be mindful of this minus sign, because of course I'm going to end up getting the negative of this 2x before all is said and done. Okay, so negative 285.8 times 6 is equal to negative 1,714.8 plus, let's see what a negative 393.5 times 4 is, a negative 1,574. Okay. Now, of course, 6 times 0 is 0, so this is going to be minus 2x, all right, is equal to a negative 1,366.8. Okay. Notice I'm not trying to do too much in one step. Just keep it slow. Keep it slow, and you should be all right. Just so now I'm going to combine the 1574 and the 1714.8. And I get a negative 3,288.8 minus 2x is equal to a negative 1,366.8. I'm going to add that negative 3, well, I'm going to add a positive 3,288.8 to both sides. I get negative 2x is equal to minus 1,366.8. Let's see, 1,922. Okay, so of course I divide both sides by negative 2. And x is equal to, divided by negative 2. X is equal to a negative 961 kilojoules per mole. Okay, so let's see, that corresponds to C, right? Okay, that corresponds to C. So that was rather entertaining problem to do. Now, number 9, we have a problem of similar ilk, I think. Let's say it's find the standard enthalpy of formation of ethylene given the following data. Heat of combustion of ethylene is negative 1,411. Okay, well, you don't really need me to do that because it's the same. You do it the same way you do number 8. So, and you have the answer key, so you know the answer. Number 9 is, the answer number 9 is A. Okay, so I'll let you guys go ahead and do that. All right, so I'll go ahead and do number 10. Number 10 says octane undergoes combustion according to the following thermochemical equation. So we have that 2 moles of octane react with 25 moles of oxygen to produce 16 moles of carbon dioxide and 18 moles of water. Now they give you the enthalpy of formation of carbon dioxide and water and octane, and they want you to calculate the enthalpy of combustion of octane. Now this problem is just like the other one. I tell you what, I will set it up, and then I will go ahead and then I'll look at what the answer is supposed to be in the answer key. Okay, because that's all you really need me to do, right? Just set that bad boy up. All right, so I'll go to the snipping tool, and then of course I'm going to paste this bad boy on my whiteboard. Let's see what we got here. So they give you the reaction, and they give you the enthalpies of formation, and they ask you for the enthalpy change for the reaction. Okay, so I'm just going to say 18, which is the number of moles of water, the stoichiometric coefficient of water, times a negative 285.8 plus 16 times a negative 393.5 times 25 times 0. Remember, oxygen, O2 gas is the most stable state of oxygen. So the enthalpy of formation is going to be 0. That's why they didn't include it. Times 2. This time, of course, they're giving you the enthalpy of formation of the fuel in this combustion reaction, which is negative 210. Okay. And then they ask you to find the enthalpy change for the reaction. So I'm just going to put an X right there. Okay. So of course, guys, this is, well, I said I wasn't going to do it, but I guess I might as well do it since it's already set up. Well, I don't know. Should I? Oh, yeah, y'all can do that. Well, just be mindful of this negative sign right here. This is a negative 210 times 2, which would be 420. The negative of a negative is a positive, so that's going to be a positive 420. And let's see what I have right here. 18 times negative 285.8 is a negative 5,144.4 plus a negative, let's see, 393. 0.5 times 16 is 6,296. Okay, so you guys get that general idea. So I'm going to say 420 minus 5,144.4 is minus 6,296 is a negative 11,020.4, which is equal to x. And of course, since I'm adding and subtracting, this is only good to 0 digits to the right of the decimal point, so it's negative 11,020, which would be A. Let's see what we got here. Going back to the whiteboard, to the study guide. Number 11. Now, what I would like you to notice is this reaction here, the difference between this reaction and this reaction. So this is a precursor to the Hess's law. Okay, it's not a Hess's law problem, but it's a precursor. Okay, remember, if you flip a reaction around, if you make the reactants products and the products reactants, then you have to change the sign on the enthalpy change for that reaction. Okay, if I multiply reaction times the constant, then I multiply that enthalpy change by a constant also. Okay, and then the other thing with Hess's law, you can add reactions up together. If you add them up together, then you of course add the resulting enthalpy change. But we're not going to add any reactions up together. All I'm going to do is I did something to this reaction to get to this reaction, and we're trying to find out what that something is. I took 2 moles of aluminum plus 3/2 moles of O2, and it resulting in 1 mole of aluminum oxide. Okay, in this reaction, I started with 2 moles of aluminum oxide, and I ended up with 4 moles of aluminum and 3 moles of O2. So it's obvious that I flipped the reaction around. I made my reactants products and my products reactants. Okay, so I know I'm going to have to change the sign on this enthalpy right here. This enthalpy. So it's going to be a positive 1,670. But I also multiplied the reaction by 2. Notice there's 1 mole of alumina right here, and I have 2 right there. There are 3/2 moles of O2 right here. I have 3, and there are 2 moles of aluminum, and right here I have 4. So I'm going to take the negative off, make it positive, and multiply it by 2. So 1,670 times 2 yields 3,340. Okay, a positive 3,340. So the answer is, of course, A. All right, E. See how easy that was? So now we're going to do a full-blown Hess's law problem, at least I think. Let me see. Calculate the standard enthalpy of formation of methanol. Okay, now these Hess's law problem, they're pretty fun to work out. Let's see what we got here. Okay, so this is the reaction we want, and of course these are the reactions we get to manipulate. We can flip them around, multiply them by a factor, add them up together, and we'll somehow get this reaction. And every time we do something to one of these reactions, we're going to have to do something to the enthalpy changes. Again, I'll say if we have to flip a reaction around, we're going to change the sign on that enthalpy change. If I multiply it by a constant, then I'm going to multiply the enthalpy change by a constant. And if I add the reactions up, I'm going to have to add the enthalpy changes up. Now, what I told you guys is concentrate on the things that you need to get and not on the things that you don't need to get. So what am I saying by that? Now, notice in this reaction right here, I have carbon in the form of graphite plus H2 and O2, and it yields methanol. Okay, so this is the enthalpy of formation for methanol. Notice that I have a 1 right there, and even if I have to have fractions on the reactant side, it doesn't matter. Okay, now what I would like you guys to consider, I'm not going to concern myself with anything that's not in this equation, in this reaction right here. For example, carbon dioxide. Okay, I'm not going to worry about the carbon dioxide. It's just going to take care of itself. Okay, and even the things that are in here that I have in more than one of these equations. For example, I have O2 in all three of these equations. I would go crazy trying to keep track of the O2, ensure that I end up with half a mole of O2 on the reactant side. So I'm not going to worry about O2. I'm not going to worry about O2, and I'm not going to worry about carbon dioxide. I'm just going to worry about carbon, graphite, H2, and methanol. All right, so the first reaction, I see that I have carbon graphite in it, okay, and I have carbon graphite in the reaction above, right? 1 mole. They're both reactants, so I'm going to leave this reaction the same. The second reaction, I have H2, all right, but I need 2 moles of it, and I only have 1 mole, so I know I'm going to multiply this reaction by 2. Right, I'm going to multiply this reaction by 2. In this reaction right here, I have methanol in it, but it's a reactant. I need it to be a product. So I'm going to flip this reaction around. So I'm going to keep this reaction the same, multiply this reaction by 2, and flip this reaction around. And I'm going to, of course, do the appropriate, make the appropriate changes or augmentations to the enthalpy. Okay, so I'm going to say carbon graphite plus O2 yields CO2. Now that enthalpy change under standard conditions is a negative 393.5 kilojoules per mole. Okay, and then you go ahead and you say the second reaction, that's the one that I have to multiply by 2. So I'm going to say 2H2, but you have to multiply all of the stoichiometric coefficients by 2. So 1/2 by 2 would be 1. So that's 1 mole of oxygen yields 2 moles of H2O. So the enthalpy for this new reaction, of course, is just negative 25.8 times 2, which would be a negative 571.6 kilojoules per mole. And let's see what we have here. The third one is the one that I have to flip around. I'm going to make my products reactants. Carbon dioxide plus 2H2O yields, let's see what we have here, methanol, CH3OH plus 3/2 moles of O2. The enthalpy change for that reaction is, since I flipped it around, I'm going to make that a positive 726.4. Positive. Okay, so now I get to cancel a few things out. Okay, even though I told you not to worry about the carbon dioxide, that doesn't mean you're not supposed to cancel that out. And I'm going to cancel out some of the O2. So notice what I have here. I have carbon dioxide, 1 mole as a product. I have 1 mole as a reactant in this equation, so the carbon dioxide cancel out. Let's look at water. I got 2 moles of water right here as a product, and I have 2 moles of water right there as a reactant. Moles of water cancel out. Now let's look at oxygen. I have 1 mole of oxygen right here and 2 moles of oxygen right there as reactants, and I have 3/2 moles of oxygen as a product. So of course 2 is the same as 4/2, so I have 4/2 moles of oxygen on my reactant side and 3/2 moles of moles of oxygen on my product side. So that of course is 1/2 mole of O2. So I'm going to go ahead and say 1/2 O2. Then let's see, I know the carbon in graphitic form comes over, okay, plus, let's see, H2, I got 2 moles of H2 plus 2H2 from right there, plus my 1/2 mole of O2, and I end up with CH3OH, and as you guys can see, that is the reaction that I was trying to get. So now all I have to do is add these enthalpy changes. So I'm going to say a positive 726.4 minus 393.5 minus 571.6. Delta H is equal to a negative 238.7. Okay, so my answer is a negative 238.7, and that would correspond to B, wouldn't it? Okay, so you guys get the gist of this. All right, so I'm debating whether or not I'm going to do number 13 or not. Okay, Number 13 is another Hess's Law problem. Of course, you're trying to find the enthalpy change for this reaction right here, and they have these two. It should be a simple matter. The first reaction, I'm going to keep the same. The second reaction, let's see, what am I going to do to that? I'm going to reverse it. Why am I going to reverse it? Because notice what I have right here. I have 21 moles of oxygen as a reactant. This reaction, I have 25. And I know I'm going to keep this one the same. So that means I'm going to have to take this O2 to the other side, and I'm going to need 4 of them to cancel out 4 moles right there. So I'm going to reverse this reaction and multiply it by 4. So that means I'm going to change the sign on this and multiply this one by 4. Okay, so that means I'm going to take 566 times 4. That would be 2,264 minus 11,020. That would give me a negative 8,756. That would be B, right? So the answer to 13 would be B. Number 14, let me see. And let me see. Okay, I'm not going to do number 14. That's just, you know, like I never should have added it. Because we've done something like this before, haven't we? They want us to get the enthalpy change for this reaction, and they give us the enthalpy of formation of the products and our reactants. And of course, they didn't give it to us for O2 because it's an element in its most stable state. But you guys know how to do that. And let's see, number 15, given a thermochemical reaction, SO2, 2 moles of SO2 plus O2 yields SO3, 2 moles of SO3. They give you an enthalpy change. How much heat is evolved when 600 grams of SO2 is burned? They give you the molar mass of SO2. All right, I'll go ahead and snip that bad boy because we need to do this. Okay, so this would be one of those problems I put on the exam on that second page. Make it worth 5 or 6 points, right? Okay, so given the thermochemical equation. All right, so now notice that this is a negative 198 kilojoules per mole of reaction. So it's a negative 198 kilojoules per 2 moles of SO2, or per 1 mole of O2, or per 2 moles of SO3. Since they asked us about SO2, then of course we're going to use the fact that it's a negative 198 kilojoules per 2 moles of SO2. So the first thing we want to do is convert grams of SO2 to moles via the molar mass. So I know I have grams, and I know I have 1 mole per 64.066 grams. I'm going to say 1 mole per 64.066 grams. And that's going to be 600 divided into 64.066 equal parts. And that's going to give me 9.365342 moles. Notice that I use a lot of significant digits, and I encourage you guys to do that too. Don't round prematurely. Okay, this is moles of SO2. So I'm going to, if I have times a negative 198.00 kilojoules, it's very important that you remember this, per 2 moles of SO2. All right, why did I put the 2 here? Because the stoichiometric coefficient in front of the SO2 is 2. So I release a negative 198 kilojoules per every 2 moles of SO2 that react. Okay, so when I get 9.365342 times a negative 198 divided into 2 equal parts, I end up with a negative 927.1689 kilojoules. And let's see how many significant digits this bad boy is good to. Let's see. I have 5 in the negative 198.00 term. I have 5 there. And in my molar mass, I have 1, 2, 3, 4, 5. So this is good to 5 significant digits. So my answer is negative 927.17 kilojoules. Okay, so if I react 600 grams of SO2, it's going to be an exothermic reaction, and I'm going to release negative 927.17 kilojoules of thermal energy into the surroundings. So that corresponds to B, doesn't it? Wait, what the hell? There's a positive sign in front of B. Wait, let me see. Did I do something wrong? How much heat is evolved? Okay, so when they say evolve, they're saying take the absolute value of it. But yeah, the answer is B, but it still should be a negative in front of it. Okay, right? Yeah, we got it right. Okay, and that is the answer. And the answer to 15 is, of course, B. All right, so I'm